Hi, in this video we're going to look at estimating the size of our error when we use Taylor or Maclaurin expansion to estimate something. So we're going to use the Maclaurin expansion for sine of x to estimate the value of sine 0.1. Now, since we're estimating a value that is pretty close to zero, the Maclaurin series centered at zero is a good one. So what we have, I'm going to put the first three non-zero terms here. So f of x is approximately equal to x minus x cubed over 6 plus x to the power of 5 over 120. Now, what I'll note here is that because these terms alternate, I'm going to alternate between having an underestimate and an overestimate. So if this, for example, were the true value of sine 0.1, my first estimate is going to be over. X is 0.1, that's going to be too much. But my next answer will subtract something and overcorrect, but it will be absolute value terms, it will be closer to the true value. Then I will add and overcorrect. I'll have an overestimate, but again, closer. Then I'll have another underestimate, closer to the true value. So we're kind of oscillating with an overestimate, underestimate, overestimate, underestimate. So with what I've got here, I will have an overestimate because I'm ending on an addition, and my next term would subtract something off. So I will have a number that's slightly too high, but hopefully pretty close. So if I want to approximate this value when x is 0.1, it is 0.1 minus 0.1 cubed divided by 6 plus 0.1 to the power of 5 divided by 120. Now, you might ask yourself, well, why would I bother using this to estimate? I have a calculator. If I have to use a calculator to um, type these values in and evaluate it, then why not just use a calculator to type sine of 0.1? But the reality is that this is essentially how calculators are doing it. Not exactly this, but similar methods, approximation methods, are used in programming in order to estimate these values. So if I type this in, I get approximately, and we'll take three significant digits. So let's go 0.0998 is the approximate value I found here. Now, if you're curious, when you do type this into your calculator, if I do type in sine of 0.1 to my calculator, all of the digits I get are 0.099833416665. And if I want to compare that with what I got when I typed in this polynomial, I got 0.099833416667. So you can see this is actually an incredibly close estimate. But without a calculator, I don't necessarily know that. So we're not going to estimate what the actual error is. We're going to estimate an upper bound on the error. So if I think this was term 1, term 2, term 3 here bouncing around, term 4 is going to be closer to the actual value than term 3, which is the one I found. But the distance, the absolute distance between these has to be bigger than the error between the value I've calculated and the true value. So what we want to figure out is essentially what's the difference between had I used an extra term on this polynomial. So instead of using just 3, what if I had used x minus x to the power of 3 over 6 plus x to the power of 5 over 120 minus x to the power of 7 over 5040? If I had done that instead, then what I would have ended up with, so let's type that on. So I've got minus 0.1 to the power of 7 divided by 5040, and that gives me, well, basically the same thing. That actually gives me, if I look at all the digits, it gives me the precision that the calculator is capable of for sine of 0.5 anyway. But the idea here is that what I'm looking for is the absolute value of the error. Oops. The absolute value of the error here is going to be the absolute value of the difference between what happens when I calculate with T4 versus what happens when I calculate with T3. The only difference between those two is the fourth term. So in other words, the absolute value of x to the power of 7 over 5040. Well, negative that, but because it's absolute value. So the absolute maximum error I can have is 0.1 to the power of 7 over 5040, which 0.1 to the power of 7 divided by 5040 is an incredibly tiny number. It's approximately 2 times 10 to the power of negative 11. So what that means is my answer is definitely within that distance of the true answer.